This is the part where the MC tries to get the pronunciation of names right and then hopelessly fails because this time it's Polish. It's Michał.
Yeah, Michał.
Kostrubiec.
Kostrubiec.
See, I think I get it right, but I don't.
Close enough.
Yeah, thank you. You're a contributor to Rust C, right?
A tiny bit here and there.
Yeah, okay. And you're famous for your Reddit posts?
Well, could you repeat?
Yeah, you're famous for Reddit posts?
Yeah, I write blog posts like teaching people kind of a tiny bit about my work related to the Rust compiler, about kind of how Rust C works in general. That's like also the goal of this talk, to kind of
super awesome.
Intrigue you a tiny bit in how the Rust compiler works, to kind of point you to. I feel it's a very interesting subject, the Rust compilation.
And you're going to do 2 talks?
Yeah, 2 talks. So.
Well, good luck.
Pressure is on, definitely.
Yeah, exactly. Good luck with the first one. Hey,
yeah.
Take it away.
So, thank you very much. In this talk, I will tell you about my work compiling Rust to C. My name is Michał Kostrubiec, and I am a 90-year-old student at the Maritime University of Szczecin, Poland. I have learned Rust in 2020 during the lockdown, and I have been working on this project for about 1.5 years, maybe soon 2. And your very first question may be, why would anyone want to compile Rust to C? Rust is a safe language and C is not, so going sort of the wrong way may seem kind of pointless. However, there is surprisingly a use case for this, so let me explain some of my reasoning. The main goal of the project is better platform support. Currently, there are quite a few systems that are not supported by Rust, and that's not because no one wants to support them, that's because LLVM doesn't support them, and in some cases even GCC doesn't support them. Like in the case of a lot of those systems, the only way to get any code running there at all is to use a proprietary C compiler, which is not ideal if you want to write something in Rust. And at first you may think, okay, we cannot run Rust on some platform that no one has heard of in 30 years. What's the big deal? Surprisingly, a lot of those systems are not nearly as obscure as you may think or wish. To give a more concrete example, recently over on the Git mailing list, there have been some discussions about moving parts of that version manager to Rust. But it was quickly pointed out that doing so would mean dropping support for the no-stop OS system. That's like a fault-tolerant OS used heavily in finance. And the Git, I believe the Git platform support policy is a bit wobbly here, but in general, they don't want to drop support for anything. So they really cannot move anything too critical from C to Rust without either, they would have, like, I don't know, maybe keep 2 implementations in parallel. It would be like very awkward. So for now, I believe they have decided to only write new things in Rust. And it's a real shame because they have some really good points around that mailing list about what benefits Rust could bring to Git. However, if we had some way of turning any Rust code into undefined behavior free, equivalent C code, this problem would kind of disappear because we could then translate Rust to C, feed that C into that platform's proprietary C compiler, and get Rust running on a lot of systems. Obviously, there are some caveats. There are some systems that are way too obscure for Rust to run on, but in general, we could get a big chunk of new targets at a relatively low cost. It's not a very simple process, but it's doable. And additionally, this has been a learning opportunity. This project actually originally started with, like, I didn't think I would finish it. I thought, okay, I would just try writing something related to the Rust compiler because I wanted to learn how it works. And it kind of snowballed from here, and I have been working on this, like, more or less daily for about those 1.5 years now. And I have been trying to teach people about the Rust compiler because I am of the opinion that a lot of people overestimate how difficult working on compilers are. They feel kind of impossible to work on because they are very big. But if you focus on a small part of the compiler, if you really put your heart into it and spend the time necessary to learn to get the hang of things, then after some time you will actually be able to contribute to the compiler quite easily because it's not difficult, it's just very big. So I have been writing a series of blogs, and it's also, as I said, the purpose of this talk is to show you a basic overview of the Rust compiler and maybe kind of encourage you to try contributing yourself. I feel if my work indirectly causes even one more person to contribute to Rust C, then I have done something with my life. Additionally, compilers are just ridiculously fun to work on. I would be lying if I said this wasn't mainly a passion project. Really, there's no word to describe this unique feeling you get when you see Rust running somewhere where isn't supposed to run on at all. I got Rust running on a Game Boy console, or I even got it for April Fools running on TempleOS. I don't know if you have heard of TempleOS. but Rust is now running the like those. Yeah. So really, as I said, like I want to kind of share this feeling with you, maybe infect you with my passion for compilers, because I feel it's like one of the most fun things you can work on. Now that I have kind of said why, I think it's important to say how, because at first you may be kind of skeptical. Rust is not known for being a simple language. It has a lot of features. And writing a whole Rust compiler as one person would be impossible. But there are some things that make it slightly easier for me. So first of all, the Rust compiler is modular, even though it's kind of split into three parts. You have the front end, that's what parses your code, and does things like macro expansion. You have the compiler middle, which is responsible for things like type and borrow checking, and the compiler backend. That's actually what creates the final executable. And the compiler backends can be actually replaced at runtime. It may come as a shock to you. You can replace entire components of the Rust compiler simply at runtime. You pass it the right flag, tell it, please load me this library and use it as a code gen backend. It will happily do so. And to write a Rust to C compiler, I don't need to write a whole compiler. I only need to write that one specific part of the compiler. This may still seem quite hard, but the way compiler backends are designed makes this a whole lot easier. So a compiler backend doesn't actually work directly on Rust code. It works on something called mir. You can kind of think of mir as a simplified representation of a Rust program. So one big Rust function will be actually split into like a whole lot of mir statements and terminators. Those are primitive operations, so array indexing, addition, function calls. And all of those things are simple in isolation. And since mir is fully borrow and type check, I don't need to worry about things like lifetimes, generics, how iterators are implemented. Like all of that, all of the things above mir are actually an implementation detail to me. I don't need to worry about them at all. They are irrelevant to my project, and all I need to worry about is mir. That also means that new features, when new features are brought to the Rust compiler, I usually don't have to put in all that much work to add support for them, because they quite often compile down to the exact same mir statements. So since, for example, I believe that enums and closures use some of the same machinery. And because of that, adding support for things like async and for future features is relatively easy. Like right now, I believe updating to a new native version, usually like I need to change something like a couple lines of code every month or two. So it's not too difficult to keep up with the newest Lightning. I don't know if I'm at the newest Lightning right now, but I know that I'm usually at most like a week or two behind. And translating mir to C is made way easier because each component of mir can actually be handled fully in isolation. Like they are not really context dependent. So if you have a sequence of mir operations, a given operation will always more or less translate to same C. It doesn't matter where is it in the function. And a given, for example, there's something called a projection, which refers to some place in memory that will also get translated to more or less the same C operations, no matter where it is placed. So I need to write simple code that handles every single one of those components in isolation, and then they get combined down into something much larger. And this is what actually enables a project like this to exist at all. Because if I am able to look at each small part of the compiler in isolation, they become way more manageable. Like taking everything that there is into having all of this in the head would at the same time would be impossible, but focusing on a single part is way more feasible. So that might have been a lot. I have introduced a lot of new concepts. So I think we will kind of look at the journey of one simple Rust function for you to get a hang of how those things look. I will show you first the original Rust code, and then I will show you the mir, talk about some of its properties, and then we will look at this generated C for you to maybe not fully understand the process, but get a gist of how things are working. So here we have a pretty simple Rust function. It consists of just one expression, and it computes the component or field-wise sum of two vectors, which represent a point in 3D space or a direction. We, for example, want to add a direction, so we add its x component and assign it to the x field of the result, or we add the y field and assign it to the y field of the result, and so on. And I feel like I don't need to explain this code all that much more. It's fairly simple Rust, fairly standard syntax. But now we will take a look at the generated mir for it. I hope that you can see everything there is there, because as you can see, the mir is quite a bit longer. Why? Because one complex Rust operation, one expression has been compiled down to a whole lot of steps. And The first interesting thing you may notice is that the return terminator at the very end here, it doesn't take in any value. So you may ask, well, what does it return? It always actually returns the local number 0. Locals in mir are referred to by numbers and not by the names. So like this actually simplifies some of the optimization work, I believe. And you may here notice that the addition of each field has been separated out into a separate statement. So when we add the X components, it is a different statement than adding the Y components. And as you can see, those operations are very, very primitive. Like I don't think there's anything simpler than a binary operation. And here later we create an aggregate, and then there's also a separate operation. So really, all of those complex Rust operations get compiled down to a whole bunch of those simple primitive things. And this, as I said, means that things like iterators get compiled down to some branching and function calls. Like there is no concept of a for loop or a while loop or an if statement on mir level. It all gets compiled down to like gotos and something called switchings, which are basically a way of implementing switching on values in mir. And now we will take a look at the C code I have generated from this mir. And you may notice that there is the exact same number of local variables, because at the beginning of the process, I actually try to keep the mir and the generated C as close as possible. I try to keep the local variable numbers as close as possible. This is once again something that simply makes my work easier and makes debugging this whole thing easier. If I can take a look at the mir and the C I generated from it, I can kind of more or less eyeball if I'm doing something right or wrong. Another thing you may notice is that sometimes I am actually unable to compile one mir statement to one line of C code. Here we have the initialization of the return struct value. This actually simplifies some stuff because enums require initializing enums using as literal in C would be a bit difficult, I believe, because you need to both initialize the variant and the tag, and it would get all messy if I try to initialize it all at once. And additionally, I believe it improves compatibility with some old C compilers. I have seen compilers which don't actually support the literal. I believe I'm not sure if it's in the first version of the C standard stack literals. I believe they may not be in it. So this actually also improved compatibility besides being a tiny bit simpler. And now we'll get kind of into what I believe to be the meat of the talk, so-called nasal demons or undefined behavior. This is actually something that my project kind of its success hinges on it a lot. Because I don't want to ever translate valid Rust code into invalid C code. But before I talk about undefined behavior more in depth, we kind of need to establish a baseline for what undefined behavior is, because I have talked to quite a few people and I was shocked at how many people don't know what undefined behavior actually means and how many misconceptions about it are out there. Some people believe it simply means that you will get some kind of undetermined result, that you may get different results between platforms. Some people think you will always crash with undefined behavior. And some people will just kind of do things like read uninitialized memory and say, oh, you will just get a random value out. Spoiler, you will not. Here we have a fairly simple Rust function that we add 1 to a certain value and check if it's the value incremented by 1 is smaller than the original value. This will actually only return true in the case of an overflow, because we have overflow, so the largest possible number becomes the smallest possible number. And at first, your intuition may be to translate it more or less into line by line to C code that looks identical. Here we are only change a few things. Those are more or less identical, save for a few syntactic differences. And you may ask yourself the question, well, is the result of the operation the same? Will this test? Will the assertion still pass? And the problem is, it sometimes may and it sometimes may not. Because a really undefined behavior happens when, at least I like to think of it as us violating some kind of rules of the language. The language is specified in a certain way that things will work, something will or will not happen, and we violate those rules. For example, if you try to mutate an immutable variable, it's obviously wrong, because the compiler can use the fact that it's immutable for optimizations. And here, when we turn optimizations on, this function can actually be optimized to always return false. You may wonder why. Well, the only way for this function to ever return true is for an integer overflow to happen. And in C, signed integer overflow is set to be undefined. So if the compiler can assume it never happens because it's a compiler for C. And in valid C, there may be no sign overflow. It's not a compiler for something that kind of looks like C. It's a compiler for C. And it's not like the compiler is not doing anything wrong. It's actually doing something right, let's say, because we want our compiler to be able to optimize things. Like, as I said, we want the Rust, for example, with the Rust compiler to be able to optimize things based on the aliasing rules. We want for it to be able to see that reading from an immutable reference will return the exact same value. We want without undefined behaviors, optimizations cannot really work because the compiler needs to assume certain things to be always true. Like it cannot assume that our variable will not be mutated by someone else, or it can assume that certain things simply may never happen. And here it assumes that an overflow may never happen. Because if an overflow can never happen, then this function will actually always return false. So this is a fully correct transformation, and it will not break any valid C programs, but it may break invalid ones. And I think the devil in the detail is that it may break. It doesn't have to necessarily break it. You may run this test on all sorts of different compilers, and some of them may optimize this, some of them may not. Different versions of the same compiler, different combination of flags. All of that may affect if the undefined behavior will actually cause trouble or not. And even in theory, the compiler could even check if it's Monday and only break your program in such a case, because it would never break valid C programs, so it would still be fully standard compliant. And so undefined behavior is undeterministic, and it can lead to all sorts of issues. First of all, incorrect behavior. Here we have seen a pretty good example of that. The end result of the program is not what we would expect it to be. And it can lead to memory unsafety, it can lead to crashes, and it can lead to vulnerabilities. Because, as I said, if we break some of those rules and the compiler optimizes based on that, it could, for example, optimize away some kind of security check. If we imagine that we, for some reason, use that function from the last slide for, I don't know, authentication, to check if the ID of a user is equal to int max, the compiler could optimize that away to always return false, and our program would be broken. Some kind of security critical stuff may be broken. And the interesting thing is that safe Rust is undefined behavior free, like safe for compiler bugs like CVRS. Rust code is considered to be undefined. Safe Rust code is considered to be undefined behavior free. Otherwise, it's not sound. And if you can actually invoke undefined behavior in safe Rust, that would be a compiler bug, and it would get reported and would get fixed. If you can do the same thing with the library, it should get reported and should get fixed. So really, the translation process must produce undefined behavior free C code. If it does introduce any kind of undefined behavior, then, well, I should just pack up and go home, because this project will not go anywhere. Currently, right now, 96% of the core compiler tests should pass with undefined behavior checks enabled. So that does not necessarily mean that there is no undefined behavior left, because undefined behavior is insidious, and as I say, the more I learn about C, the less I know about C. Because there are quite a few things that are undefined behavior but are not exploited by most compilers, or by our compilers I have access to. So is it undefined behavior if compilers don't exploit it right now? Well, it still is, but it's not really a problem. Or the undefined behavior checks, they only kind of check for the most common kind of undefined behavior. They don't check for all possible undefined behavior. There are some things that may slip through them. Yeah, I have also seen with some compilers they detect undefined behavior only when you, for example, enable some optimizations. So really, squashing all the possible undefined behavior may be verifying that I for sure produce undefined behavior free C code is quite a task. I don't know if I will be able to ever say with confidence that there is no undefined behavior there, but I can say that I have put a lot of effort to minimize that risk at least. And yeah, so that's, as I said, undefined behavior will screw us over. If there is any undefined behavior in your program, there will be issues at some point in time. Oh, we can see here a little bug. Oh well. So let's kind of look at some ways we can avoid undefined behavior, because Some of it is quite ugly, but for a lot of problems, actually, the solution is relatively simple. It's like you will be able to understand why those solutions work. They may not be pretty. They may have some overhead. Okay, thank you. They may have some additional overhead. They may be quite ugly. So let's start first of all with signed and over and underflow. So the funny thing is that in Rust, the signed and unsigned variants of operations are actually identical if you look only at the bits of the value. That means that if you ignore the type and you only look at the bits that compose the value, they will be identical. And if you look at the instruction that in most cases the compiler will use, they will be identical. So we can, instead of performing a signed addition here, we can simply replace it with unsigned addition. And this is actually fully sound, and from what I have checked, most C compilers will simply translate it to the correct instructions. There will be actually very little to no overhead to this. So this is a nice example of a case where we can avoid undefined behavior with relative ease, and where we don't need to pay any additional costs to prevent it. Another thing that can cause undefined behavior are bit shifts. So in C, if you shift something by an amount larger than the size of an integer, the result will be undefined. But in Rust, you will either get a panic or you will get a shift by the modulo of the amount. So here we have to actually add something to the C code, but it's actually a cost that the Rust compiler pays to in a lot of cases. So this is an example of where undefined behavior makes the generated C code slightly more complex, and I think some C compilers may not be able to eliminate it in all of the cases, this additional modulo, but it's, as I said, if it is a cost that's also paid by the Rust compiler, it's not really a cost we pay. Like in the end, the performance between the C code that got compiled to native code and the native code created by Rust C is more or less the same. And one thing I have actually seen that a very few people know that casting a floating point value outside of the valid range is actually undefined behavior. And this actually has led to some interesting bugs in the real world. I don't know if you have heard of the game Mario for the Nintendo 64, the first 3D Mario game. You can actually crash it in quite a few ways by because that particular system, I believe, traps when you try to cast a float value out of range. So if you try to cast a too large of a value, you will actually get a crash on those systems. And on other systems, you may get a wraparound. On some, it may saturate. So there are as many systems there are that many completely different behaviors in regards to this. And as I said, it's undefined behavior. So if you, for example, do this kind of cast, the compiler may later assume that the floating point value is actually in the range, and since it sees that if it was out of range, you would have undefined behavior, can actually remove subtract later on. So this is once again the case where undefined behavior may be viral. That's like one thing that's, I think, very important to understand here, that undefined behavior can actually affect pieces of code that seem completely unrelated. So my solution for this is fairly stupid. We simply check if the value is outside of that range and return int max or int min. It isn't the cleanest thing ever, but it works. We actually also use here a simple none check, because since none is not equal to itself, we can simply check for all values that are not equal to itself, and this way we'll actually quite cheaply detect none. This actually can still cause problems if you turn on some optimizations in, I believe, fast math, for example, in GCC, because in those cases the C compiler can actually assume that nuns don't exist. So that would be even more of a trouble. But like you actually have to ask for this trouble. So I don't, and there really isn't any way for me to avoid that, save for, I don't know, emulating floating point values or something crazy like that. Yeah. Intrinsic, and this is like one of the funniest cases of undefined behavior for me, because the count leading zeros intrinsic is actually quite simple. All it does, it counts the number of zeros at the beginning of a number. So here, for example, it will return 0 because there are no zeros in that number, or it will return 31 because the first 31 like digits of that binary digits of that number are actually zeros. But if we call it with a 0, that's undefined behavior. And you actually, the C compiler in a lot of cases catch that and even warn you about that. And the reason, you might wonder, like, why on earth would this be undefined behavior? Why, like, this seems like, what would be the benefit to making this undefined behavior? Actually, the problem is that on architecture level, the bit scan forward instruction, I believe, is set to produce not undefined, but an unknown result if you pass 0 to it. So on the CPU level, the instruction itself is set to, it can produce something else than you may expect. And this is actually, from what I've heard, like through the grapevine, that's one of the reasons why this intrinsic is actually undefined behavior for 0. So yeah, CPUs can have kind of their own version of undefined behavior too. Yeah, so now I will kind of wrap things up, start kind of summing things up. I have gone over like the simpler cases of undefined behavior. I have actually kind of considered going over some more complex ones, but I feel like I wouldn't have the time to give them justice. I will like quickly mention some of them later on. So the only reason a project like this can exist is because the Rust compiler is highly modular. Like if it was designed in a different way, if there was no way to replace a backend, something like this couldn't exist. I think for sure with only one person, like I would need probably at least as many people as are currently working on the Rust compiler to kind of recreate it. So the only reason I can do something like that at all is because the Rust compiler is modular. And despite being called unstable, from my experience, the compiler internal APIs that are exposed are actually fairly stable. That's one good thing about them. Like they are, even though they may not be always perfectly documented, the one good thing about them is they tend to be stable. They don't tend to change all that much. And because Mir is so much simpler than Rust, I don't need to worry about a lot of high-level detail. I can simply ignore that. I can only worry about, as I said, a small part of the compilation process, and I can ignore quite a bit of the complexity. Here, really, I think the biggest lesson for me from the project is to kind of work on focusing on a certain scope and to not kind of exceed that. The biggest challenge for the project is, as I said, undefined behavior, and it makes sense because Rust is not C and C is not Rust. They have different semantics, different things. There are actually cases where something is not undefined behavior in C but is undefined behavior in Rust. Those are quite weird, but they do happen, and there are cases where something is undefined behavior only in C. So really, the translation must preserve those semantics of Rust as well as possible. I have actually also fused my backend with a tool called Rustlantis. It actually generates a whole bunch of compiler ER, and I use that to kind of more ensure correctness. Additionally, like it's not perfect, but since it was used actually to detect bugs in the upstream Rust compiler, it has actually detected, I believe, 20 or so of them. So I believe that I did a much smaller fuzzing campaign, and I haven't found anything yet. Maybe that's the case of someday I need to throw more compute at that to like find those cases. But in a lot of cases of an undefined behavior, we actually have simple zero-code workarounds. So for example, with overflows, as I said, they compile down to the same instruction. So really, there is no need to worry about that. In other cases, we have some overhead, like with bit shifts, like it's an overhead that's actually also paid by the Rust compiler, but there is overhead. There are some other cases, like with intrinsics, or like to quickly mention about the count leading zeros intrinsic. Actually, the Rust compiler has two variants of this intrinsic, one for non-zero values and one for zero values. That's because it actually needs to insert a check just like that. So the check I have inserted for non-zero values, that's something the Rust compiler will actually insert too, because of the bit scan forward instruction. On more modern CPUs, it will actually use an instruction that implements the intrinsic for all values in a fully defined manner, but okay, I digress. Certain kinds of undefined behavior are way more complex to work around. For example, I know that some people who are more in the know will be very curious about strict aliasing, because that's kind of a big elephant in the room. Strict aliasing basically allows C compilers to assume that certain kinds of pointer will not alias. The general simplified idea is that if you have pointers to different types, they will not overlap. So if you read a pointer from an integer, the pointer from a float will point to a different allocation at the same time. Okay. And in this case, the workaround is kind of ugly. I just need to use memcopy for all memory loads and memory writes. As I said, it's not pretty, but it works out. Yeah. And like this will be, I'm kind of wrapping out now, but I see that I have slightly more time. So to mention another thing, right, because I this is something like people ask me about, like precede some questions. I actually preserve debug information in the generated C code. I use something called the line directive to preserve source file information. So if you use that debugger, it will actually point at the Rust code. And like as I said, the main goal of my project is to create C that's undefined behavior free, and if possible, that looks also similar to original Rust code to allow you to quite easily verify that. So yeah, if you have any more questions, you can actually find me anywhere in the conference. And like feel free to just go up to me. I will, since I'm one of the Gossip people who got the Gossip Spotlight, I also have a table at which I will be sitting during most of the breaks. So you can just come up to me, ask any question you may have about anything, and I will try to explain that. And I believe, do we have like time for questions now? Okay, so like if you have like
Nice.
Thank you, Michał. Well, great talk. Should we do some questions? Is Arya going to throw the catch box?
Arya, you got it?
Where are the compiler nerds at?
I think I can probably guess the answer, but do you do anything about the max symbol name limit in C versus mangled symbols?
Yeah, actually, like in such a case, I was have something to like. I don't truncate them, but because that leads to collisions, I have to first I hash the symbol and then I use the symbol hash. If like it's very very long, in such a case, I replace it with like an encoded hash of the symbol, and that tends to work out. Like I haven't seen like a collision with that yet, but you would have to have a lot of symbols for there to be a collision in such a case. But yeah, it's kind of sad that I have to do something like that, but I have a limit. That's like configurable. I can kind of, I believe right now it's a constant, but I can raise it or lower it depending on C compilers, because I have actually seen some C compilers. There's actually, with symbol names, there's actually a lot of work between different C compilers, because some of them allow some symbols like the $sign. So some C compilers accept that, but some of them only accept ASCII characters. So I have actually an option to like lower our symbols to only use ASCII. Yeah.
Okay. Want to do a question here?
You already know about a lot of potential theoretical problems when going from Rust to C, but there are probably some blind spots you may not be aware of. So when you get your C output, how do you test that what you have obtained is reliable? How do you find new blind spots to work on and to patch further?
That's actually a pretty good question. As I have kind of alluded, I run the Rust compiler test suite, and I kind of cross my fingers and hope that by running that much code, like a lot of those are actually written to test different pathological cases. There are some really, really weird things out in the compiler test suite. If you like look at the passing test, there's a test called Zombie Jesus or like something like that. So there's like a lot of really weird tests that test really weird edge cases you wouldn't think of, like comparing the addresses of function pointers and things like that. So they, because I believe back in the early days of Rust, things like there were actually some issues with aliasing. I believe the Rust compiler didn't emit the no alias attribute because there were some LLVM bugs that caused miscombination in such cases. So there are a lot of like tests that test this kind of thing. So the hope is that I will catch most of them by running those tests with undefined behavior checks on. I also, as I said, I fast the compiler a tiny bit. I have my own tests written for some things that I know that tend to I have my own regression test that I like run on every commit to like ensure that I don't break anything, because I have in the past broken things in some ways that I didn't expect to break. Yeah, there are definitely like a lot of really, really weird edge cases that I have to kind of go over it. And hope is, as I said, like there's no, if I find something weird, then I just add it to my test suite, and it kind of is growing over time. I have 400 or 500 of tests of my own. Yeah.
Okay. Are we doing on time?
I think we can do 2 more questions.
Okay, cool.
Up over there.
Here. Hello. You've nearly found me. That's okay. I am curious about how big your project is, and also how big it was when you had the first successful compilation.
depends on what you mean by successful compilation.
Oh, just the very smallest piece of Rust that generated valid C code.
It was like, I think, the 300 or 400 lines of code that were needed to start the backend. That was at the very beginning when I compiled a simple function that just added two numbers together. Right now, I'm kind of in an awkward spot because I'm doing a very big refactor right now. I have made, as I said, it's a learning project, and I have made some very stupid mistakes in the past that I'm kind of trying to dig myself out of the holes I dug. So I think it's like 40,000 lines of code, but a lot of it is duplicated because I am moving from one representation of C to another that's like way more optimized. I started with kind of a stupid representation that doesn't do any interning, and I'm adding things like interning right now. That basically means that it allows me to save on memory. Yeah, so I think like at least 10,000 lines of code is duplicated between the old and new implementation, and I'm kind of slowly ripping that out as I kind of work around some issues. But another interesting thing is that actually most of the code is shared between my work compiling Rust to C and work compiling Rust to .NET. I believe the difference between the code compiling Rust to .NET and Rust to C is like only a couple thousand lines of code in the very end of compilation. Most of the process is actually shared, and that like makes some things easier.
And the compiling to .NET is what your other talk will be about.
Yeah.
So the ecosystem track, if people are excited about that.
So like, if you are not bored of my voice already, I recommend you go there.
Do we have one more question somewhere? I don't know where the box is. I can't see anything.
Yeah. So I got a question here. Maybe is that okay?
Yeah. If the box is not in somebody's hands.
Hi, thanks for the talk. Do you plan on supporting unwinding at any point?
I support unwinding for the .NET part of the project, but I haven't looking like into how to do that in C, and it like looks like there's some compilers that have their own extension. Like, right now, I basically compile unwinding to the equivalent of the .NET mechanism for try-catch, and if a compiler supports something like try-catch, I can support unwinding. In such a case, I have actually my own implementation of libunwind, like a mock implementation that implements all the functions necessary for Rust work. But adding full unwinding support requires C compiler to support that, and then I think MSVC has something like that with structured exception handling, but that's only one compiler, and there are some like restrictions, so I haven't actually looked into that quite yet. I have kind of once such, as I said, like it needs the C compiler to support some things, and not a lot of them do. So for now, I just kind of you have to abort on panic. With .NET, you can actually recover from a panic, but with the C side of stuff, sadly, there's just no good way. Maybe someone will tell me that maybe there exists a way. Maybe I'm just blind and I didn't notice something. But right now, I don't think there's simply a good way to do that.
Sounds like you need to compile to C++ or something.
Yeah.
All right. Thank you so much for your talk. Give it up for Michał.